When European engineers saw the 15-ton planer arriving at the Cincinnati factory in 1911, they declared it a catastrophic waste of money. 60 years later, manufacturers were tearing apart closed factories just to find one. How did the machine they called obsolete become impossible to replace? December 1911, Cincinnati, Ohio. The foundry doors of Cincinnati Planer Company barely accommodated the flatbed railcar carrying what critics would soon call Morrison's Folly. 53-year-old Daniel Morrison stood in freezing rain, watching riggers position the 15-ton cast iron bed of his newest creation. A planer designed to machine locomotive frames, ship engine beds, and the massive steel plates that modern industry demanded. The bed alone stretched 20 feet long, its single casting weighing more than 3 complete European planers combined. Morrison had built his reputation on practical solutions, not theoretical elegance. Starting as an apprentice machinist in 1876, he'd spent 35 years understanding what machines actually endured in production environments. Now, as chief designer and partial owner of Cincinnati Planer Company, he was betting his career on a machine that violated every principle of modern efficiency. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. The European manufacturers had already solved planing, or so the technical journals insisted. German engineers at Ludwig Löwe & Company had perfected rapid traverse planers that completed strokes in half the time of American machines. Swiss manufacturers offered precision, ground ways that eliminated hand-scraping labor. British designs incorporated lightweight construction that reduced material costs while achieving speeds that American heavy iron could never match. The mathematics seemed irrefutable. A European planer completing 60 strokes per minute would finish work twice as fast as an American machine limited to 30 strokes. The Continental designs weighed less, shipped cheaper, and occupied less factory floor space. Most compelling, too. Cost-conscious manufacturers, they required smaller electric motors, reducing both initial equipment investment and ongoing power consumption. Morrison's planer contradicted this efficiency gospel. Where European machines used 4-inch table ways, Morrison specified 12-inch hand-scraped surfaces. Where German designs employed 800-pound cutting heads, Morrison built a 3D 200-pound tool holder that machinists joked could plane through a battleship's armor. The drive mechanism alone, a massive gear train powered by a 50-horsepower motor, weighed more than some competitors' complete machines. Standing beside the partially assembled planer, Morrison traced his fingers along the hand-scraped ways. Each square inch had been carefully worked by master craftsmen, creating bearing surfaces that would guide the table through millions of cutting strokes. Critics called this labor-intensive finishing outdated craftsmanship that precision grinding had rendered obsolete. But Morrison had calculated something the efficiency experts missed. In metalworking, the force required to remove material increased exponentially with depth of cut. A machine taking shallow passes might run quickly, but a machine capable of heavy cuts would remove more steel per hour despite slower speeds. Could Morrison's massive planer prove that brute capability mattered more than optimized velocity? The criticism arrived before Morrison's planer completed its first production cut. Dr. Friedrich Zimmermann, technical director of Stuttgart Machine Works, published a detailed analysis in American Machinist magazine that dissected every aspect of Cincinnati's new design. Zimmermann's mathematics painted Morrison as either ignorant of modern engineering or deliberately resistant to progress. His calculations demonstrated that Morrison's 15-ton planer consumed 3 times the floor space of equivalent European equipment. The massive construction required foundation in work that added $2,000 to installation, costs money that could purchase an entire second European machine. The slow stroke rate of 30 per minute, Zimmermann argued, meant Morrison's planer took twice as long to complete any given workpiece. In an era when manufacturers measured efficiency in output per labor hour, this represented catastrophic competitive disadvantage. Factory owners reading Zimmermann's analysis questioned whether American manufacturers could compete globally while clinging to obsolete construction methods. European technical institutes had revolutionized planer design through systematic study of cutting dynamics. At the prestigious ETH Zurich, Professor Hans Scherer had developed optimization equations that balanced machine weight against cutting capability. His research proved that lightweight construction with rapid traverse speeds maximized productivity while minimizing material and energy costs. German manufacturers had implemented Scherer's findings with impressive results. The Ludwig Lohe type, 4-planer, weighing just 5 tons, could complete a 6-foot stroke 60 times per minute. Its precision groundways hardened to 60 Rockwell provided accuracy measured in 10,000ths of an inch, without the human variability that hand scraping introduced. Ball-bearing slide mechanisms reduced friction to nearly zero, allowing smaller motors to achieve higher speeds than American designs with their plain bearing ways. Swiss precision added another dimension to European superiority. Oerlikon Machine Works had perfected hydrostatic bearing systems that floated the planer table on pressurized oil films. These systems eliminated metal-to-metal contact entirely, promising unlimited service life without the wear that plagued traditional sliding ways. The technology represented everything modern engineering could achieve, scientifically designed, precisely manufactured, and optimized for maximum efficiency. Morrison read Zimmermann's critique in his office overlooking the Cincinnati factory floor. The German engineer's conclusions seemed inescapable. Morrison had built an expensive dinosaur that would bankrupt any company foolish enough to purchase it. Several potential customers had already canceled orders, swayed by Zimmermann's authoritative analysis. But Morrison had witnessed something the efficiency experts had not. He'd watched European planers tackle the heavy steel plates that railroad shops and shipyards actually needed machined. He'd documented the multiple shallow passes required, the frequent tool changes, the vibration that destroyed surface finish. The optimized machines performed beautifully within their design limitations, but real production work exceeded those limitations daily. Would Morrison's massive overbuilt planer prove that theoretical optimization failed when confronted with practical metalworking demands? Morrison's design philosophy emerged from a brutal lesson learned 15 years earlier. In 1896, he'd witnessed a supposedly modern planer destroy itself while machining a locomotive bed frame at the Chesapeake and Ohio Railway shops in Richmond. The machine, a lightweight German import celebrated for its efficiency, had been taking increasingly aggressive cuts to meet a production deadline. The 12-inch thick steel plate required material removal measured in cubic inches per minute, not the delicate shavings that European demonstrations featured. Midway through the stroke, the cutting head deflected under force, gouging the workpiece and snapping the tool holder mounting bolts. The tableways, precision ground to eliminate hand-scraping labor, showed visible scoring where the deflected head had scraped across them. Morrison had watched master machinists attempt repairs that ultimately proved impossible. The groundways couldn't be restored without returning the entire machine to the manufacturer in Germany. The lightweight construction that made the planer economical to ship also made it impossible to retrofit with stronger components. After 6 weeks of attempted repairs and $8,000 in expenses, C&O Railway abandoned the machine and returned to their old American planer, a crude, heavy iron beast that simply refused to break. That experience crystallized Morrison's thinking. Optimization theory assumed controlled conditions and predictable forces. But real manufacturing involved material variations, interrupted cuts, tool deflections, and operators pushing machines to their absolute limits. The question wasn't whether a machine could handle ideal conditions, but whether it could survive the abuse that production environments inevitably delivered. Morrison's approach inverted conventional engineering logic. Instead of calculating minimum requirements and adding safety factors, he designed components that made failure mechanically impossible. The planer's 15-ton bed wasn't sized to handle expected forces. It was sized to laugh at forces that would destroy lighter machines. The massive cutting head didn't just resist deflection under normal loads, it remained rigid under emergency conditions that would snap lightweight tool holders. The hand-scraped ways represented another philosophical departure from modern efficiency. Precision grinding produced surfaces accurate to millionths of an inch, but grinding created work-hardened surfaces prone to sudden failure under overload. Hand scraping created softer, more forgiving surfaces that wore gradually rather than catastrophically. More importantly, Hand-scraped ways could be restored in any machine shop, while ground ways required factory service. The gear-driven table mechanism continued Morrison's theme of indestructible simplicity. Where European designs used friction drives and hydraulic systems that optimized for speed, Morrison specified massive helical gears cut from solid steel forgings. The gear teeth were sized for loads 10 times greater than the 50-horsepower motor could deliver, ensuring that mechanical failure would never occur during the machine's service life. Could this philosophy of deliberate excess prove more valuable than the scientific optimization that dominated contemporary engineering thought? The pattern shop at Cincinnati Planer Company revealed Morrison's philosophy transformed into three-dimensional reality. Master pattern maker Robert Kellerman supervised construction of the wooden forms that would create the sand molds for the massive castings. The bed pattern stretched across the entire pattern shop floor, 20 feet of carefully shaped wood that represented 6 months of skilled labor. Every rib, every web, every bearing surface had been precisely formed to create internal geometry that distributed stress through the entire casting. Kellerman understood what Morrison demanded. Not just a heavy machine base, but a structure engineered to absorb forces the way a cathedral's flying buttresses distributed weight. The foundry operations required capabilities that few American facilities possessed. The bed casting alone needed 22,000 pounds of molten iron poured into a sand mold weighing over 40,000 pounds. The pour had to be completed in under 4 minutes to prevent premature solidification, requiring multiple furnaces timed to deliver metal simultaneously. Master foundryman Heinrich Weber coordinated the pour with the precision of an orchestral conductor. 6 furnaces, each containing 4,000 pounds of iron heated to 2,850 degree Celsius, moved into position around the massive sand mold. Weber's signal triggered simultaneous pouring from all 6 crucibles, filling the mold with gray iron that would take 8 days to cool completely. But cooling was only the beginning. After the casting emerged from the sand, it underwent a stress-relieving process that set Morrison's design apart from competitors who rushed castings directly to machining operations. The bed spent 72 hours in an annealing furnace heated to 1,000 then cooled at a controlled rate of 50 degrees per hour. This thermal treatment eliminated the internal stresses that caused castings to warp during subsequent machining, ensuring dimensional stability that would last decades. The machining operations revealed why Morrison specified tolerances that seemed excessive for a machine tool. The bed's table ways, those 12-inch wide surfaces that guided the reciprocating motion, were first rough-milled, then finish-milled, then hardened through flame treatment, and finally hand-scraped by master craftsmen who spent 3 weeks per machine achieving bearing surfaces accurate to 0.0001 inches across their entire 20-foot length. The cutting head assembly demonstrated similar attention to inherent capability rather than optimized efficiency. At 3,200 pounds, the head incorporated dovetail slides 8 inches wide that provided vertical adjustment through hand-operated screws with 10 threads per inch precision. The clapper box, the mechanism that lifted the tool on the return stroke, was built with clearances measured in thousandths rather than the loose fits that European rapid traverse designs employed. The drivetrain represented mechanical engineering unconcerned with space or weight restrictions. Helical gears, 16 inches in diameter, transmitted power through shafts measuring 4 inches across, creating a mechanical advantage that could push the 6-ton table through cuts that would stall optimized machines. Could Morrison's approach of building beyond any conceivable requirement prove its value when production demands exceeded theoretical calculations? The validation Morrison sought arrived through a contract he hadn't pursued. In March 1913, the Brooklyn Navy Yard issued specifications for machining armor backing plates, 3-inch thick nickel steel sheets measuring 12 feet by 8 feet that would support the main belt armor on the new Pennsylvania-class battleships. The material properties alone terrified conventional machinists. Nickel steel heat-treated to Bayou-5 Rockwell, hardness possessed tensile strength exceeding 120,000 pounds per square inch. Cutting it generated forces that destroyed ordinary tool holders and vibrations that shattered carbide inserts. Previous contracts had required multiple European planers working in tandem to complete the work, each machine taking shallow cuts that accumulated slowly toward the finished dimensions. Morrison saw the specifications as the ultimate test of his design philosophy. He submitted a bid claiming that a single Cincinnati planer could complete the work faster than multiple European machines, while maintaining flatness tolerances of 0.005 inches across the entire 12-foot length. The Navy's engineering officers dismissed Morrison's bid as either delusional or fraudulent. Their experience with armor plate machining had established clear limitations on what planers could achieve. The Brooklyn contract manager, Commander Robert Fitzgerald, USN, had personally supervised numerous armor machining operations. His data showed that planers could safely remove nickel steel at depths not exceeding 0.40 inches per pass. Attempting deeper cuts produced tool failure, surface damage, and machine deflection that destroyed accuracy. Morrison's proposal specified cuts reaching 0.125 inches deep, more than triple the accepted maximum. Fitzgerald's response letter outlined why Morrison's bid violated physical reality. The cutting forces at that depth would exceed 8,000 pounds, causing deflection in any machine tool ever built. The vibration would destroy surface finish, and the heat generation would warp the workpiece. Morrison's claims represented either fundamental ignorance of metalworking principles or deliberate misrepresentation to win the contract. Rather than argue through correspondence, Morrison invited Navy inspectors to witness demonstration cuts on test plates identical to the contract specifications. 3 naval engineers, Commander Fitzgerald, Lieutenant Charles Morrison, no relation, and civilian metallurgist Dr. Kenneth Weaver, arrived at Cincinnati in April 1913, prepared to document the failure that would vindicate their skepticism. The test plate, measuring 8 feet by 4 feet and 3 inches thick, sat on the planer table surrounded by measurement equipment that would document every aspect of machine performance. Morrison adjusted the cutting head to 0.125-inch depth, engaged the 50-horsepower motor, and started the first pass. The massive table began its 8-foot stroke at 30 strokes per minute while the tungsten carbide tool bit into hardened nickel steel. The Navy inspectors prepared their instruments to measure the deflection and vibration that their experience guaranteed would occur. But the indicators remained motionless as continuous steel chips curled away from the cutting edge. Could Morrison's overbuilt planer actually achieve what naval engineering experience insisted was impossible? Commander Fitzgerald's measurement instruments recorded performance that contradicted his 15 years of naval metalworking experience. The planer table moved through its stroke with no detectable deflection. The cutting head remained rigid under forces that should have bent the tool holder. Most remarkably, the finished surface showed flatness within 0.003 inches, exceeding the contract specification while removing material 3 times faster than accepted practice allowed. The test continued for 6 hours, machining the entire 8-foot by 4-foot test plate in a single setup. Dr. Weaver's temperature measurements showed the workpiece remaining within 12 degrees of ambient throughout the operation, eliminating the thermal distortion that plagued multiple pass machining. The cutting tool, a tungsten carbide insert that typically lasted 90 minutes on European planers, remained sharp after 6 hours because Morrison's rigid machine eliminated the vibration that destroyed cutting edges. Lieutenant Morrison, who shared surname with Daniel, Morrison created continuous confusion, documented production rates that transformed naval procurement calculations. The single Cincinnati planer completed work in 6 hours that required 18 hours on the European equipment currently installed at Brooklyn Navy Yard. The heavy cuts eliminated the multiple setups that consumed time and introduced dimensional errors. Most significantly, a single machine operator could manage the entire operation rather than the 3-man crews that European rapid traverse planers required. The economic analysis revealed advantages that efficiency theory had missed. Morrison's planer cost $28,000, substantially more than European machines priced at $18,000. But the single Cincinnati planer replaced 3 European machines while reducing labor requirements by 6%. The cutting tool lasted 4 times longer, and the machine's inherent accuracy eliminated the inspection rejects that plagued lighter equipment working beyond their design limits. Commander Fitzgerald faced a conclusion that contradicted his engineering education and practical experience. The slow, heavy, expensive planer that violated optimization principles actually represented superior value for naval production requirements. Brooklyn Navy Yard immediately ordered 2 Cincinnati planers and began planning to replace their entire European equipment inventory. The production statistics from the Pennsylvania-class armor contracts validated every aspect of Morrison's design philosophy. From July 9, 1913 through November 1914, the 2 Cincinnati planers machined 340 armor backing plates with 0 rejections for dimensional errors. The European planers working on the same contract produced 220 plates with 18 rejections, despite having 4 machines dedicated to the work. Tool costs dropped 75% compared to European equipment because carbide inserts survived the vibration-free cutting conditions. Floor space utilization actually improved despite the planer's massive size because the machines eliminated the staging areas where workpieces waited between multiple setups on lighter equipment. Morrison's obsolete design had proven that real production efficiency came from capability rather than velocity. But would the metalworking industry recognize this truth? Or would optimization theory continue to dominate machine tool procurement decisions? The aftermath of Morrison's vindication reveals an engineering lesson that resonates across a century of technological development. By 1920, Cincinnati Planer Company couldn't manufacture machines fast enough to satisfy demand from shipyards, railroad shops, and heavy manufacturing facilities that had finally understood what Morrison had known all along. The production statistics told a story that optimization theory couldn't explain. Factories replacing European planers with Cincinnati machines reported productivity increases averaging 6%, despite the American equipment's slower stroke rates. The massive machines simply worked continuously, taking cuts that would have destroyed lighter equipment, maintaining accuracy that eliminated rework, and surviving conditions that sent optimized machines to the scrap heap. The most remarkable validation came decades later. During the 1960s, when manufacturing had supposedly progressed beyond crude mechanical advantage, procurement managers at major steel mills began searching for used Cincinnati planers from the 1911 era. The machines had survived 50 years of continuous service, while European planers from the same period had long since worn out and been scrapped. Modern CNC technology brought new capabilities but couldn't overcome the fundamental physics that Morrison had understood. Computer control could optimize cutting paths and speeds, but it couldn't replace the mass that absorbed forces without deflection. CNC planners achieved precision through sophisticated measurement and compensation algorithms that corrected for machine deflection. They were solving in software what Morrison had eliminated through overbuilding. The ultimate irony emerged in the 1980s when manufacturers of heavy CNC planers began advertising enhanced structural rigidity as a premium feature. These machines employed massive cast iron construction, large cross-sections, and hand-scraped ways, precisely the characteristics that engineers had mocked as obsolete in 1911. The premium CNC planners cost 5 times more than standard models, yet they were simply relearning Morrison's lesson that heavy construction enabled capabilities that optimization could never achieve. Contemporary machining proves Morrison's philosophy remains valid. When manufacturers need to plane large steel plates, machine cast iron engine blocks, or flatten aluminum aircraft components, they frequently discover that 1911-era Cincinnati planers outperform modern equipment. The century-old machines maintain their original accuracy, absorb forces that cause computer-controlled planers to trigger overload alarms and complete heavy cuts that modern lightweight construction cannot handle. The hand-scraped ways that Zimmerman dismissed as outdated craftsmanship show less wear than precision-ground surfaces from machines built 60 years later. The massive gear drives that optimization theory claimed were inefficient still deliver reliable power after millions of cutting strokes. The 15-ton construction that seemed absurdly excessive has proven to be exactly sufficient for real metalworking demands. Morrison's 1911 planer demonstrated that sometimes the machine engineers call obsolete is actually the one built correctly from the start. But here's the question that challenges every modern engineer. If we learned this lesson over a century ago, why do we keep building machines optimized for theory rather than reality?